Every large cargo ship you've ever seen places its bridge at the stern. Most people assume it's about forward visibility. It isn't. On a vessel like the Ever Ace, carrying nearly 24,000 containers, moving the superstructure forward would erase over 1,000 container slots and $2.7 million in revenue per voyage. This isn't a design quirk. It's the outcome of an engineering revolution that began with one ship in 1965. Most people, when looking at a massive cargo ship, expect the bridge to be up front, like the cockpit of an airplane or the cab of a train. It feels natural to assume the captain needs the clearest possible view ahead. In fact, international safety rules even back up that instinct. The SOLAS Convention, which governs nearly every commercial ship in the world, sets a minimum forward visibility requirement. The officer on watch must be able to see the sea surface at least 500 meters ahead from the bridge. For passenger ships, a common industry guideline is a 120-meter clear sight line over the bow. That figure, 120 meters, often gets repeated as the hard rule, and it is easy to imagine that meeting it would demand the bridge be placed as far forward as possible. But the reality on modern cargo vessels is very different. The bridge sits at the stern, sometimes perched 40 or even 60 meters above the waterline, far from the bow and behind rows of containers stacked 8 or 9 high. On a fully loaded, ultra-large container ship, the captain's direct view of the bow itself can be blocked by hundreds of meters of cargo. Yet these ships still comply with international visibility standards, not by moving the bridge forward, but by raising it high enough to see over the entire deck. Regulations are satisfied through bridge elevation and advanced navigation systems, not by sacrificing cargo space for a forward command post. So while the instinct to put the bridge up front is grounded in both logic and regulation, the solution that dominates today's shipping industry defies that expectation. The reason isn't just about what the captain can see, it's about what the ship can carry and how efficiently it can move goods across the world. The transformation of ship design in the 1960s was driven by the sudden rise of containerized cargo. Early container ships, like the ACT-1, launched in 1965, still followed the old formula: bridge and crew quarters near the middle, engine room aft, cargo holds in between. But as global trade demanded ever more standardized 20-foot containers, these traditional layouts quickly ran into hard limits. Every meter of deck broken up by a superstructure or a midship bridge was a meter lost to revenue-earning cargo. The ACT-1's midship bridge forced a split in the container bay, limiting both capacity and efficiency. Shipyards and naval architects responded with a radical solution. By 1969, the Maersk Mac entered service with its bridge, crew spaces, and navigation equipment all consolidated at the stern, directly above the engine room. This new aft superstructure layout allowed for a continuous, unobstructed stretch of container cells from bow to stern. The impact was immediate. Cell bays could be stacked higher and run the full length of the hull, while cranes could operate efficiently without needing to work around obstacles. This wasn't just a matter of rearranging living quarters. The move to the aft bridge solved a pressing engineering and commercial challenge of the container age. It unlocked a step change in cargo capacity, streamlined loading operations, and set the new standard for every major shipbuilder. By early 1970s, the aft bridge configuration had become the blueprint for the modern container ship, a direct response to the demands of the global shipping boom. Ever Ace stretches 400 meters from bow to stern, with a staggering capacity of 23,992 TEUs, 20-foot equivalent units. Each of those steel boxes represents not just a slot on deck, but a direct line to shipping revenue. On the Asia-Europe route, a single TEU commands about $1,500 in freight charges per round trip. Multiplied across a ship fully loaded to capacity, that is over $35 million in revenue for just one voyage. Now consider what happens if the bridge and superstructure are moved forward. The physical footprint of a forward bridge, along with the necessary crew accommodations and safety clearances, carves out a block of space that cannot be filled with containers. On a vessel the size of Ever Ace, this translates into a loss of about 1,080 TEU slots, roughly 4.5% of total capacity. That is not an abstract percentage. It is a loss of $1.6 million in freight revenue for every round trip, just from the cargo that no longer fits on board. Over the course of a year, with a typical schedule of 10 round trips, the missing slots add up to $16 million in foregone earnings. These are not hypothetical numbers. Charter rates and slot utilization are tracked daily by shipping lines and investors. Every container slot is a unit of profit or loss. For ultra-large container ships, even a small reduction in capacity has an outsized impact on operating margins. The economic case for keeping the bridge and superstructure at the stern is not just about tradition. It is about preserving every possible slot for cargo, and in turn, every possible dollar of revenue. The design is a direct response to the relentless drive for efficiency and profitability in global shipping. Aft engine placement delivers a mechanical advantage that's hard to overstate. The propeller shaft is the critical link between the main engine and the water, turning raw horsepower into forward motion. On a modern container ship with the engine room at the stern, the shaft can be as short as 30 meters. Compare that to a midship engine layout, which stretches the shaft to 120 meters or more. That extra length isn't just a matter of more steel, it's friction, energy loss, and ongoing maintenance. Every additional 50 meters of shafting adds about 0.8% to shaft line friction. For a 120-meter shaft, that's a 1.9% increase in fuel consumption compared to the short, direct drive of an aft engine setup. On a vessel burning 150 tons of fuel per day, that translates to nearly 3 extra tons per day, thousands of dollars lost on every voyage. Over a year, the penalty can exceed $1.5 million in fuel costs alone. The energy wasted fighting friction is energy that could be moving cargo. Maintenance follows the same logic. Longer shafts mean more bearings, more alignment checks, and more time spent in dry dock. Industry data points to a 15% reduction in shaft line maintenance when the engine sits aft. Fewer moving parts, less wear, and easier access all add up to lower operating costs and higher reliability. For the crew, a shorter shaft means less time spent monitoring vibration and temperature, and more time focused on safe, efficient operations. This isn't just theory. Classification societies and ship owners track these numbers closely, because even a small improvement in fuel efficiency or downtime can tip the balance in a market where margins are razor thin. The mechanical case for the aft engine, aft bridge layout is grounded in physics and in the relentless math of global shipping. Raising the bridge high above the deck solves the visibility challenge on today's largest cargo ships. On ultra-large vessels, the bridge sits as much as 40 meters above the waterline, roughly the height of a 12-story building, deliberately engineered to clear even the tallest stacks of containers. This elevation isn't arbitrary. It's calculated to guarantee a direct line of sight over the entire cargo field, meeting the International Maritime Organization's SOLAS requirement for at least 500 meters of forward visibility. But clear vision from the bridge windows is only part of the equation. Modern navigation depends on electronic systems that continuously scan the ship's surroundings. Automatic Identification System, AIS, transmits and receives vessel positions every 2 seconds. ECDIS, the electronic chart display, and radar systems provide real-time mapping and object detection up to 30 nautical miles ahead, regardless of fog, darkness, or heavy rain. These technologies work together to deliver a level of situational awareness that far exceeds what the human eye alone could manage, ensuring that even from the stern, the bridge is fully equipped to meet both regulatory and operational demands. A crane operator working a modern container terminal faces a simple equation. Every obstacle on deck slows down the job. With the bridge and superstructure placed at the stern, gantry cranes can sweep the entire length of the vessel without pause, reaching up to 30 container moves per hour under optimal conditions. That difference is not just theoretical. On a busy Asia-Europe route, saving 45 minutes of berth time per ship call, thanks to a clear, uninterrupted deck, can free up an additional vessel slot in the terminal schedule, translating into as much as $1.2 million in annual value for a single ship. Compare this with the operational realities of ferries, cruise liners, and tankers. Ferries and cruise ships prioritize bow visibility for tight maneuvering and frequent dockings. Their bridges sit forward, above the vehicle ramps or passenger decks, because docking speed and direct sight lines matter more than squeezing out extra cargo slots. Tankers, on the other hand, keep the bridge aft to leave the deck open for pipelines and cargo manifolds, not containers. Each vessel type is shaped by its mission. For ultra-large container ships, the stern bridge is the linchpin that maximizes deck efficiency, port throughput, and ultimately the economics of global trade. Every aft bridge container ship crossing the world's oceans today is a testament to relentless engineering logic, not tradition. As cargo volumes grow and navigation systems update positions every 2 seconds, efficiency and regulation drive design. The next revolution in shipping will demand even more from these floating machines. Share your thoughts below.